Hey guys, this video is about, it's just a quick video on the solutions to the second question for coursework number 2. We have a group of order 24 and we have to prove that it's solvable. Okay, and our strategy is to start with a C-log 2 subgroup. Okay. And this strategy is actually from, like this question was one of the, an assignment question, but not to be handed in. And this hint is from that assignment. So let's take P, be a C-log 2 subgroup. Okay, and now what is the size of P? Well, to find out, we have to factorize 24. 24 is 2 cubed times 3. So any C-log 2 subgroup has 2 cubed elements or 8. Okay. And now what did the hint say? The hint said, let's take X to be the cosets of P in G. Okay. And let G act on X by left translation or left multiplication. So we'll define G times XP. Well, it's just the coset of GX. That's for all G and for all cosets. Okay, remember P is maybe not normal in G, so these left cosets, you don't have a group, you just have some, like, you just have the sets, right? This is just a set of left cosets. Okay, so this gives us a group action. What's the number of elements in the set? Well, it's just the size of G divided by the size of P. In other words, 24 over 8, just 3. Okay, so X has 3 elements. We have a group action on a set with 3 elements. Now that gives us a homomorphism from G to basically the permutations on the set X. Well, X has 3 elements, so we really get permutations in S3. And what is the definition of phi? Well, G gets mapped to the permutation, and what permutation? Well, it's the permutation that sends X, the coset XP, to GXP. Okay. Okay, so we get phi is a homomorphism. Okay, that's pretty good. What do we know about a homomorphism? Well, the kernel of a homomorphism is a normal subgroup. What else do we know about this kernel? Well, it is actually contained in P. Let's see why that is. The kernel of phi, well, an element in the kernel of phi is those elements of G which give a trivial permutation. So there's those G's such that GXP equals XP for all X. Okay, and this is a subset of those G's such that GP equals P, because instead now I've relaxed this condition. Instead of for all X, I just say for where X equals the identity, and if X equals the identity, you just get GP equals P. But that's just the entire group P. Okay, so the kernel of phi is contained in my C-log 2 subgroup. scroll down. So that means the kernel of phi has 1, 2, 4, or 8 elements. Okay. But also, by the first isomorphism theorem, G mod the kernel of phi is isomorphic to phi of G. Phi of G is sitting inside S3. Okay. S3 has 6 elements, so phi of G has at most 6 elements. This is a 6, not a G. In case it's so close with my handwriting. Anyways, okay, so we have 6 elements. The kernel of phi has either 1, 2, 4, or 8 elements. Okay, so let's look at, of course, this has 24 divided by the kernel of phi, number of elements in the kernel of phi elements. So if the kernel of phi equals 1, then G mod the kernel of phi, now that has, well, G has 24 elements divided by 1 element, which is greater than 6. So it's not, this can't happen. Similarly, if the kernel of phi has 2 elements, well, then the number of elements in G mod the kernel of phi is 24 over 2, which is 12. Again, that's bigger than 6. Okay, so again, this can't happen. So that's the possible number of elements in the kernel of phi. Okay. And what does that tell us? Okay, let's write down a few things we know now. First thing, the kernel of phi is a 2 group. Oh yeah, let's write as G. It's normal in G. Okay. The kernel of phi is solvable. What else? G mod the kernel of phi equals, like, it's a divisor of 6, so it's either 1, 2, 3, or 6. Actually, the kernel of phi is not any of these. It can either be 3 or 6. It's 3 if the kernel of phi has 8 elements, and it's 6 if the kernel of phi has 4 elements. Okay. And now we need to know that groups of order 3 and 6, or I should say are solvable. Groups, kernel of phi is solvable since 2 groups are solvable. Okay, so to see that a group of order 6 is solvable, you can just, it's not too hard. So let me just add that on to the end after I finish this argument. So let's see. So now we know that the kernel of phi and G mod the kernel of phi are solvable. So G is solvable. Okay, and let me explain to you quickly. Well, that's the end of the question, but let me explain to you quickly how we might argue that a group of order 6 is solvable and G be a group of order 6. Let P be a CLOF 3 subgroup Okay, now P has 6 is just 3 times 2, so P has 3 elements. So P has index 2, so P is normal in G. P and G mod P are solvable. So G is solvable. Okay, so any group of order 6 is solvable through a quick argument. And so now we, for sure know that any group of order 24 is solvable. Okay, so the next thing will be the third question on the coursework. Thank you for watching.